Chapter 6.3 and 6.4 discuss intermolecular forces and solubility. While the last video discussed a little about these intermolecular forces and how they help you predict melting points and conductivity, we can go a little bit further than just discussing whether something is ionic or covalently bound together. So to begin with, we have our first intermolecular force, which is called dipole-dipole interaction. And basically, if you have a compound that is covalently bound and yet it's polar, then it can have what's called dipole-dipole bonding. So while the strongest intermolecular force is that ionic compound, if you do have a covalently bound compound, then which covalently bound compound is going to exhibit stronger bonding? That is a question that can only be answered by looking at the interactions between molecules within a solution. So this is an example of dipole-dipole forces. And so if you think about like a sugar cube, it'll line up in certain ways. Salts, they will have a certain way of looking under a microscope, and so they will line up nice and pretty like this picture here where it's forces in a solid, whereas in a liquid they're a little more variable, but they're still very strong. And so the dipole-dipole is a very strong force that holds different covalently bound compounds together, or the same covalently bound compound together. So in order to figure out if a molecule will exhibit intermolecular force called dipole-dipole, you must first decide if the bond is polar. Then decide if the molecule is polar. So this goes back to those Lewis structures that we looked at before. And it also reminds us of the electronegativity values we looked at for chapter 4. And so if two molecules are bound together and they have different electronegativities, so like hydrogen's 2.1, oxygen's 3.5, that is going to be a polar bond. But then you have to also check and make sure the molecule is not symmetric. Because if that molecule is symmetric, it could be a nice tug of war where the two ends of the molecule are pulling equally. And then instead of having a very positive area and a very negative area, it's going to be nonpolar throughout the molecule. And so the more polar the compound, the stronger the intermolecular forces. And so if you notice here, like fluorine has a very high electronegativity. So if it bonds with like beryllium compared to potassium, that difference is a lot stronger for fluorine with beryllium. And so yes, that's going to be an ionic compound, but if those were in a covalent compound, that would be very, very strong. Nitrogen with fluorine or chlorine with fluorine, there's going to be an electronegativity difference where more of the electrons are hanging around the fluorine and therefore it gets that partial negative charge, and the thing that's more positive, like the hydrogen, will get the partial positive. Alright, so the next intermolecular force our book discusses is dispersion forces. And the idea behind these forces is if you have something that is nonpolar in nature. So look at the structure for these nitrogens here. They're nonpolar. There's no reason that a single nitrogen should be positively charged and the other identical nitrogen is negative charged. It just doesn't make sense. But what happens is what you see here, where the electrons start out nice and evenly distributed. There's no polarity about the molecule at all. Everything is pretty evenly distributed. Then these electrons, when they come near more electrons are going to repel each other. And so what could happen is the electrons in one molecule momentarily become more clustered on maybe the left side, and then if it comes near another molecule while that's happening, that will temporarily get a negative charge because this was positive. And so it's almost like these electrons that were all nice and evenly distributed, if they see a positive charged species near them, they'll run over to say hello. And so dispersion forces are just simply weak, extremely weak, and very fleeting forces that just occur between two nonpolar molecules. So you first have to look at molecules and decide covalent or ionic. If they're covalent, you look and say, does it have a dipole, or will only dispersion forces be dominating? And then we have another intermolecular force called hydrogen bonding. Now, hydrogen bonding is just a subset of dipole-dipole interactions, and it's a very strong subset of it. And so what happens is anytime that you have a hydrogen atom that's bound to a nitrogen, oxygen, or fluorine, it can hydrogen bond with its peers. And so in this case, if you look down here at this molecule, if you have H and F, then if it comes near another fluorine, this is a hydrogen bond. And so each of these are individual molecules, but the pink is showing you the intermolecular forces, and the specific one being hydrogen bonding. The idea that since fluorine is so electronegative, since oxygen is really electronegative, look at these electronegativity values down here in the bottom corner. They're super electronegative, and so they're going to pull those electrons really far away. So if there's a hydrogen nearby, hydrogen's going to get a very big partial positive, and the nitrogen or the fluorine or the oxygen is going to get a partial negative. And so what's going to happen is, instead of just being a strong dipole-dipole force, it's going to be extremely strong. And that's just because those electronegativity differences are so big that it's almost like it's ionically bonding. If I had to classify these as which one's strongest, I would say ionic bonding is the strongest, then hydrogen bonding, then dipole-dipole, then dispersion is the weakest. Hydrogen bonding is showing here with water, where you've got water molecules, and in water it'll line up where the hydrogens will be attracted to the oxygens of the other molecules around it. Alright, so here's an example of how you would decide, hey, what intermolecular forces are present here? So let's say this first example, if I have a butane molecule attached to a propane molecule, then these are going to be very non-covalent. I mean, very covalent, they're very non-polar. And so when they come close to each other, they don't have those polarity differences to bank upon. Instead, it's just simply dispersion forces. And so remember, anytime you have nonpolar compounds covalently bound together, the predominant intermolecular force is going to be dispersion. Here, this next example, we have hydrochloric and hydrobromic. And so if you'll notice that these small hydrogens, which are shown in white, will line up where it'll go positive for hydrogen, negative for the chlorine, positive for the hydrogen, negative for the bromine. And so those are dipole-dipole, where hydrogen bromide and hydrogen chloride are in fact, they both could be classified as ionic or covalent, but they're definitely going to have partial positive and partial negatives. And so that's going to be your dipole-dipole forces. Could they also have some of those ionic charges? Absolutely, because they are both acids. So then when we look at this one, we've got some hydrogen bonding going on, because this hydrogen finds this fluorine and they are super attracted to each other. If I were to ask you which of these have the strongest forces, I hope you would say the hydrogen bonding, then the dipole-dipole, then the dispersion. Alright, so this is a graph showing you the molecular weights of the compound along this axis and the boiling points. And what's significant about the colors is this is what happens when you go and you look at a group. So meaning, if you look at carbon on the periodic table, right below carbon is silicon, right below nitrogen is phosphorus and arsenic, oxygen, sulfur, and selenium, they all go together. So as you go on a group, what typically happens is the larger the molecular weight, the more electrons a molecule has for intermolecular forces, therefore it takes a lot more energy to separate them because their intermolecular forces are stronger. So bigger the compound, stronger the intermolecular forces, the larger the boiling point. But there are exceptions, and so if you notice, these three are my exceptions. So what is happening? Oxygen is smaller than sulfur, so why does oxygen have such a big boiling point when it's with hydrogen in the form of water? Why does fluorine so big? Why is your nitrogen bound to hydrogen so big? And if you think about it, it's because of that hydrogen bonding. The oxygen, the nitrogen, the fluorine are all involved in bonding. And so you have a couple things here in play. As the size of your atom increases, your boiling point increases. But hydrogen bonding is stronger, and so that's going to increase your boiling point even more significantly. Kind of take-home message from this is the stronger the intermolecular forces, the higher the boiling point. If you get that out of it, fantastic. But just note that how you recognize which one is the largest is by looking at size, hydrogen bonding, dipole-dipole, and then dispersion forces. But a big question I always like to think about is, why do we care about this? Well, we personally care because like dissolves like. That's a fancy way for saying that if you understand why stuff interacts, then you can help predict what will be soluble in each other. And so meaning, if you add a gasoline additive to gasoline, you better hope they're soluble. If they're not soluble, you're going to get engine knocking because you're going to have some gunk building up somewhere in your car. Okay, and so what makes those gasoline additive soluble is that it was designed with the idea that those dispersive forces forces from the gasoline are going to be very similar, and also you've got the alcohol group, which is polar, so it's going to have a little bit of polarity there. But if you have something that's super polar and you try and put something that's very nonpolar into it, they will not dissolve. You'll get a precipitant, or it'll look like this oil and water that you see here. So they're definitely insoluble, where your oil is going to be your nonpolar, and your vinegar is going to have those dispersion forces. Your vinegar is going to have your ionic as well as your dipole-dipole forces. And so when you've got the two together, they're not going to mix. And so figuring out what types of intermolecular forces something has tells you whether or not they're going to be soluble. And in this last picture, water and alcohol are both polar molecules, and so they will be soluble in each other because they'll all have, in this case, you'll have some hydrogen bonding, but then you'll also have that dipole-dipole interactions. All right, go read section 6.5.